S. Chand presents educational video lectures as per the AICTE curriculum. Difficult concepts made easy. Study anywhere, anytime.
Now, how we can resolve the two things? We are able to see the two things different from each other. So that can be seen or that can be possible by using the resolving power concept. So myself Narinder Kaur, if you want to study this topic in detail, kindly refer this book by S. Chand Publishing. All the topics are given in quite details in the given book. Now the e-book link has been given in the description box. By using the concept of Raleigh criteria of resolution, how the two things that can be resolved, we are able to distinguish the two things separately from each other. Now there comes the Raleigh criteria for resolution. Now this criteria that is used to resolve the two things from each other. So that means how you can, when we are placing the two things, they are quite near to each other. Now we are able to see these two slits as a one thing, but when again here these are the two slits, so we are not able to distinguish these two slits separately over here. And then when these two slits are separated quite far away from each other, we are able to distinguish these two slits. Then the Raleigh criteria of resolution is used in order to resolve the two things. So according to which we are able to resolve the two things when, or the two materials or the two images, because we are seeing here the 2D image or the 2D picture of the things. So the two images, they can be just resolved when the main condition is that the central maxima for the diffraction pattern of one falls on the first minima of the diffraction pattern of other. That means we are able to resolve these things. So what is this? So means if there are the two objects are placed over here, if these are the two objects, we know that when the light is falling on these two objects, we are able to resolve these two objects as a separate things. That means when the light is falling on the two objects, there occur bending of light around the corners of obstacle. That gives us the diffraction pattern, and we are able to see each and every part of the object. That means on the object, if this object is illuminated with light, because if there is no light is falling on the object, we are not able to see the object properly. Now in order to see this object properly, what we will do here? Here this is illuminated with light, then light is falling on the object. Again at each and every point on the object, there occur bending of light. So there occur bending of light and also spreading of light in its geometrical shadow. Means there occur bending and spreading of light, bending and spreading of light in its geometrical shadow, which gives us the diffraction pattern. That means from the maxima and from the minima, we are just able to see the object. So that means when we are seeing this object, light is falling on it, there occur bending of light, and on the screen we are getting the diffraction pattern. So this diffraction pattern that can be obtained. So from maxima and from minima, when the white light is falling on this object, so we will get the colored diffraction pattern over here. Then we are able to see the different colored part of the objects. So that can be seen by us. Again, there is another object. Now if these two objects, so there are the two objects. So one object and the second object. When these two objects are placed far away from each other, we are able to see them because they are resolved. How they can be resolved? Because their diffraction pattern that is resolved from each other. So they are placed quite far away from each other. so their diffraction pattern that can be resolved. That means the maxima of one in the diffraction pattern, what we will get? We are getting the central maxima, then secondary maximas and so on. So that means the from central maxima we are able to see the object. Now when these two objects are placed quite away or quite far away from each other, so in this case what will be there? If this is a point lambda 1 is here and here is a lambda 2, that means we are, one is with the wavelength lambda 1, second one is with the wavelength lambda 2. That means here we are able to distinguish these two objects as a separate object, because lambda, here the central maxima of one object that is quite far away from the central maxima by the other object. That means we are able to distinguish these two objects separately. They can be distinguished from here. But in the second thing, in the second part, when these objects are placed very close to each other, when these objects are placed very close to each other, so in that case, now if this is a central maxima of one object, now if this is a central maxima of one object, then again here this is a central maxima of other object and so on. So in this case what will happen? The central maxima of one superimpose on central maxima of other. So we are not able to resolve these two objects as a separate object. That means because their central maximas because their central maximas are almost superimposed on each other. So that means these objects, if these are the two objects, they will appear as a one object. We are not able to distinguish these objects. So this is called the Raleigh criteria of resolution. So according to Raleigh criteria, these two objects, if this is a one object and that is a second object, and they are placed very close to each other. Now if we want to distinguish these objects as a separate objects, so in that case the diffraction pattern is that the first central maxima of one, in the diffraction pattern what is the main condition? If this is a central maxima of the one object, that will keeps away from the central maxima of the other object. So they are quite different from each other. Now that means one condition is that the central or the first maxima of one falls on first minima of other. When maxima falls on the minima, that means if this is a minima of first and then here this is a maxima of, now if this is a condition over here, now in this case if this is the first minima, here this is the first minima, it falls on the maxima of other, because this is the diffraction pattern by first and that is a diffraction pattern by second object over here. So we are able to resolve these two objects as a separate object when this is a central maxima of one, it falls on the first minima of other, or you can say that this is a minima of first, it will falls on the central maxima of other. So in that case then the pattern that can be given like this. The overall pattern is like this for the central maxima. That means we are able to distinguish these two objects as the individual objects. They are taken as separately. So in this case this delta lambda, that is a difference in the wavelength of these two, that must not be equals to 0. That means when you want to resolve these two objects as a separate object, this delta lambda that is not equals to 0. So this is a Raleigh criteria of resolution according to which these two objects that can be placed separately, when first condition is that the first minima of one falls on the second maxima of other, or you can say that the first maxima of second that can fall on the first minima of other. So when maxima falls on the minima, that means you are able to distinguish these two central maxima as the individual ones. They can be distinguished separately from each other. So in that case you are able to distinguish the two objects separately. This is called Raleigh criteria of resolution. Now again, when they are superimposed on each other. So in the second case, when the delta lambda is not equal, delta lambda is equal to 0, means this is for the, if this is for the second object. So for the second object, then on give the resultant wave for these, that will becomes like this. Here the delta lambda is equals to 0. Now in this case, this central maxima that will be broadened up because these two will be added up in this case. So here the delta lambda that is equals to 0, but we are not able to resolve these two objects as a separate object. So these objects that can be resolved, that cannot be resolved over here. So the main condition for resolution is that the central maxima of one falls on minima of other, or the minima of one falls on maxima of other. When this condition is there and delta lambda is not equals to 0, we can resolve the two objects separately. Now second thing, when the objects are quite far away from each other, that means if this is the condition for one, we are able to see the objects when there comes a diffraction pattern. Diffraction pattern will come when the light falls on the object and there occur bending of the light around the corners. So in that case we are able to distinguish the object. Now if this is for the second object, now in this case you can clearly see that these two central maxima, they are quite away from each other. That means these two objects are placed quite far away from each other. So clearly we are able to resolve these objects over here. Now this is applied in order to see the diffraction pattern, or in order to see the very small sized particle from each other. We know that when there are the large number of electrons, they are placed in the atoms. How you can distinguish that one electron from the another electron? So that can be used, or that can be distinguished from each other by using the diffraction pattern, because there occur bending of the light, again there comes a diffraction pattern, and from the diffraction pattern we are able to distinguish the electrons, how they are available or they are presented the given orbital. We know that in the orbitals there are the electrons present like as 1s2, 2s2, 2p6. So this is the configuration and so on. This is the configuration of electrons. Now when you want to distinguish these electrons from each other, this kind of pattern, firstly you want to see the electron with the diffraction, and after seeing the electron you are able to distinguish these two electrons separately from each other. So this is the Raleigh criteria of resolution. So now let us take a short break. So now till now we have studied what is the Raleigh criteria of resolution, how we are able to distinguish the two objects from each other. Now after the break we will study what is a diffraction grating and its resolving power.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy. Before the break we have studied what is the Raleigh criteria of resolution. Now we will understand what is diffraction grating. That means if at a time large number of slits are present, then what kind of diffraction pattern we will get on the screen, and how we are able to resolve that diffraction pattern on the screen. That can be understood by using the resolving power of grating. So now what is the diffraction grating? Now diffraction grating, basically it is a combination of large number of slits. So diffraction, if we are able to see this, That means the single slit that can be divided into large number of parts. So these parts, they are in the thousands. That means for the diffraction grating, this single slit that is divided into large number of parts over here. Now the parts of the slits, they are basically these parts are equals to, most of the cases this is taken to here n, that is taken to equals to 1800 or the 2400. So this type of pattern, that is called diffraction grating. So that means now from each and every part there occur bending of the light. Then after the bending of light, what we will get? Then after the bending of light, we will get a diffraction pattern from each and every part. Then these diffraction pattern, after the bending of light, these they will superimpose on each other. And after the superposition, what we will get? We will get the interference pattern. Then again it can be constructive or destructive. That means diffraction grating is basically, it is an optical instrument with the periodic structure. That means it is divided into, here the width of each and every part, that is constant over here. The distance or the separation of the grating, that is constant over here. So what is the condition over here? If this is a slit in the grating, then these parts are separated by equal, and now the width of these, this is equals to constant always. So this width is constant, also this separation, that is constant. So this is a periodic structure in this case. So this is called grating here, and it is also an alternative way to absorb the spectra other than the prism, because in this case in the prism we are again same getting the diffraction pattern, bending of light around the corner. Then again here we are getting the diffraction pattern by bending of the light at each and every part. And on the screen we are able to see the resultant intensity with the, we can see the enhanced view of the diffraction pattern that can be obtained. Generally, now when the light is incident on the grating, this light will have maxima at an angle theta. We know that. That means in case of this diffraction pattern, now if this is a grating over here, means instead of single slit, now we are placing a grating. So when the grating is placed, what is grating here? So this is the, in this case n parts, they are separated from each other with equal separation, means the width of each and every slit, that is constant, and the difference between each and every part, that is equals to constant over here. Now when the light is falling on each and every part, so in this case what we will get? Here the light is incident on each and every part over here. So in this case, so that can be converted into parallel beam. Firstly, if the source is present over here, so that is converted into parallel beam by using the lens over here, then the light, then the large number of parts are available over here. So that means it is converted into a parallel beam. Now we know that at each and every part there occur bending of light around the corner, and due to bending of light, what we will get? We will get the diffraction pattern at the screen. Now at this screen, how we will get this diffraction pattern? So that can be done by using again a lens. Lens is used over here. So in this lens, the light get combined or that get converged at the single point. So that means if this O is the point of maxima over here, that means the light from each and every slit, so that get converges over here. So from the diffraction pattern, that means we here there is no need to divide the slits into n number of parts. Then after that, this light is combined. So here the light will combined over here. Now what we will get here? O point, that is the point of central maxima. Again, when there occur bending of light, or it will converge at an angle theta. So in that case, what we will get? Then at the point P, we will get the point of maxima or minima. So the secondary maxima or minima, that can be calculated for this grating. This. Now if this angle is theta for each and every end, let us suppose there are capital N number of parts. Now then the phase difference or the path difference for one part, that will be equals to, now the path difference for one part, that will be equals to, here it will come, now this will be the path difference that can be calculated by dropping a perpendicular over here. Now if this angle is theta, so this will be equals to, now if this small part is equals to E, that is equals to E sin theta. So now we know that can be phase difference, that can be calculated over here. So the phase difference by one slit, that is equals to 2 pi by lambda into E sin theta. Again we will divide this single slit into small n number of parts. Then for that case, the total phase difference phi, now if this is equals to 2 pi by lambda into E sin theta, then on dividing this single part into n number of slits means there are the large number of parts over here. So we will divide this into the small n number of parts. So in that case, the beta phase difference, that will become 1 by n into delta phi. Then we will get here 2 pi by lambda E by n into sin theta. So that will be the phase difference. Now there are 1800 number of the slits are present over here. Now let us suppose that the number of slits are present over here n. Then the total phase difference, so that can be calculated by adding up the all of phases for by all the slits. So the total phase difference, that will be equals to capital N into this beta. So that will be the phase difference by large number of slits. What is small n here? Small n is the number of parts in which the single slit is divided into the small parts. What is the capital N? Capital N is the number of parts on the grating. Capital N, that is the number of parts of the slits on the grating, while the small n is the number of parts in which the single slit is divided. The single slit is divided into small n number of parts, and capital N is the number of parts which are present on the grating. So the total phase difference, that will be equals to n into beta. So that can be written as 2 pi by lambda E by small n into capital N into sin theta. Then again by using these relations, we can calculate the resultant amplitude, that will becomes NA sin alpha by alpha. Then the central maxima intensity for the central maxima, that can be calculated, that is equals to R square. Now for central maxima, when you are calculating, we are calculating intensity for the central maxima, then I naught, that will comes n square into a square. Now in case of single slit, we are getting intensity equals to a square, but in case of grating, what is n here? N is a number of slits which are present on the grating. So in that case, we are getting I naught, that is equals to n square into a square. So this is all about the diffraction grating, how you can split the single slit into large number of slits. Then we can calculate the diffraction angle over here, that can be calculated by using this relation. What is n? That is the order of the grating, d is the distance between the fringes, lambda is the wavelength, and theta is the angle to the maxima. So by using this relation, we can calculate central maxima position and minima positions for the diffraction grating. Now next is the resolving power of grating. So firstly, what is the resolving power of a normal instrument? So resolving power is basically defined as the capacity or an power of an instrument in order to resolve the two objects. What is the Raleigh criteria of resolution? According to Raleigh criteria of resolution, two objects, they can be seen separately from each other when central maxima of one falls on minima of other. But how we can see these two objects? These two objects, they can be seen separately from each other by using some instruments. These instruments are able to resolve the objects separate from each other, and their capacity is known or measured in the terms of resolving power. So resolving power, that defines the ability of an optical instrument to distinguish between the two objects or to see them separately from each other. So that means when we want to see the two objects separately from each other by using some microscope or the telescope, so one, that is the thing by which we can see these two objects. The ability of an optical instrument, that is measured in terms of resolving power. In the similar way, diffraction grating has some resolving power in order to give, we know that what is diffraction grating? In the diffraction grating, there are the large number of slits which are placed parallel to each other, and the separation between each and every slit is constant over here. Now the diffraction pattern will be getting, we will get diffraction pattern from this slit, again from this slit. So there are a large number of diffraction pattern are obtained. After that, superposition at the screen, we will get the resultant diffraction pattern. So the resolving power of diffraction grating, it will describe how we can resolve the diffraction pattern of each and every part separately from each other. From the diffraction pattern grating, as there are the large number of parts are available, then how can we distinguish diffraction pattern from each and every part separately? That can be done by measuring the resolving power of grating. So the resolving power of diffraction grating, that is defined by this formula, that is given by, so the diffraction resolving power of grating, that is equals to lambda by d lambda, which is equals to small n into capital N. So this is defined as the resolving power of grating. What is d lambda here? Now if we want to distinguish between the objects over here, so d lambda, that will give us the difference between the wavelength of these two, when we want to distinguish between the two gratings or the two waves. So that is the difference between the wavelength is given by d lambda. What is small n here? Small n, it is defined as the number of parts in which the single slit is divided. That is a single slit parts. That is the parts of the single slit which is divided, which is given by small n. What is capital N? That is the number of slits present in the grating. Number of slits present on the grating. So by using this formula, we are able to get the resolving power of grating. That means grating is used to distinguish between the diffraction pattern of two waves, or you can say that the number of slits which are present on it. So we have studied what is the diffraction pattern of grating, how the resolving power of grating, and how we are able to distinguish between the diffraction pattern from each and every part of the grating. Thank you. This topic in detail, kindly refer this book by S. Chand Publishing. All the topics are given in quite details in the given book. Now the e-book link has been given in the description box. Now if you like the video, kindly like, share and subscribe this video, and also you can press the bell icon for the future notifications.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.